Welcome back. In the last video, we saw an example how to compute the homology of a space just from the axioms. But homology is not just a functor that assigns to an object in a abelian group, it also assigns to a topological map, so a continuous map, a homomorphism of modules. And we now want to see in examples where you can also compute Hn applied to a map. And the example I want to look at are the spheres with the reflection. So let SD to SD be the map, let's call it rho, that takes the tuple of points. So we think of the D sphere as lying in R to the D plus 1. And it takes this tuple of points to x1, x0, x2, up to xd. So it's a reflection. And we've seen that the homology in degree d of the sphere is just z. And the question we want to answer now, what about the induced map? What about this map here? Now, what can we say right away? This map rho, the reflection, is homomorphism. Its inverse is the reflection itself. So a homomorphism induces an isomorphism of the groups. So the automorphism groups of the integers is very small. It's just multiplication with 1, so the identity, or multiplication with minus the identity. Multiplication with minus 1. So minus the identity. The question is, what is it? And the claim is, the reflection is multiplication with minus 1. And we want to show this claim, again, by inductively building up. So we start with the easiest sphere, which is for us S0. There we have to modify the statement a little bit, because H0 of S0 is not the integers. It's a copy of it's a sum of two copies of the integers. But there's a similar statement valid there. And then we work from there and prove this inductively. So let's first consider S0. All right, so S0 is very, very easy to compute the homology, because it's just 2 points, and the 2 points are minus 1 and 1. So we have this isomorphism. And if we assume, which we do for this video, that H is a homology theory satisfying the dimension axiom in the form that the homology of a point in degree 0 is just C, and in all other degrees is 0, then these are 2 copies of the integers. Now, we can look at the induced map by this reflection, which in this case just exchanges the points minus 1 and 1. Okay, what is this map? Well, as I said, these are just points. So here we have C plus C. And if we identify this here with C plus C, then this map takes -1 on the space level to 1 and 1 to -1. Therefore, on the level of the homologies, it takes xy, which we think of being in C plus C, to yx. So that's the induced map after identifying this with C plus C. Then I also want to consider here a subspace of H0, S0, and the subspace I want to consider is the kernel of the canonical map, or the map induced by the canonical map from S0 to the point. And from any space, we always have a map to the point. We can look at an induced map, and here we look at the kernel, which lies inside this H0, S0. And the map rho induces also a map between these kernels, because the map rho is compatible with the projection to the point. Compatible meaning there is a commutative square where you have the map from S0 to S0 and the maps to the point. Therefore, we get also here an induced map. Let me also denote it by H0 of rho. I didn't like my arrow. And let's discuss now what this map is. So first of all, this kernel as a group is just isomorphic to C. Why is that? Well, we can maybe think on this left side what this kernel really is. Okay, so you have this map to the point, and this map to the point, what does it do? If you identify both H0 minus 1 with C and H0 1 with C, then here you have the point, which is also isomorphic to C. So this map, let me draw it here, is on this level induced by the map from the one-point space to the one-point space, which is basically the identity, and here also from -1, the one-point space, to this one-point space. And therefore, on each of these Z copies, it's just the identity. So again, thinking of an element in here as an element xy in C plus C, this is mapped to x plus y under this map. And if you want to understand now the kernel, well, the kernel consists of all elements x minus x in this sum. So these are exactly the elements that are mapped to 0 under the canonical map to the point. So if you write this also as a copy of the integers, then the map, the inclusion map, would be taking an element here to C minus C. That would be the map. And now, with all these identifications, we can see what this map rho induces on the level of the kernels. Because if you have an element here, it's mapped to Z minus C, then they get interchanged, so they are mapped to minus C, and this is coming from the element minus C. So the induced map here is just the multiplication with minus 1. And that's the first step in proving the claim above, that the induced map on HD of a sphere is multiplication with -1, which here I was thinking of d at least being 1. And for d equal to 0, we better work with this kernel because it's isomorphic to C. And there it's the multiplication with -1. So how can we...
But what does this statement above now say for d equals 0? If you can scroll down a bit again.
The statement above, I just formulated.
It's only formulated.
Just formulated for d at least 1.
Yeah. I mean, because one can ask oneself, what does the map that swaps the 2 points of a zero sphere do in homology, right?
And that's exactly what I explained.
Okay, that's okay.
That's exactly what I explained.
That's just a swapping map, x, y,
that's
to y.
That's just a swapping map.
Yeah, okay.
And if you look at this subspace, which corresponds to the elements x minus x, then swapping is multiplication with -1.
Okay.
And if you look now at a sphere SD for d at least 1, and you look at the corresponding kernel, which would now be the kernel of HD, SD to HD of a point, then for d at least 1, HD of a point vanishes by the dimension axiom, and this would be just the homology of SD. Therefore, if you want a statement here that works also for d equals 0, we could have right away said we don't look at HD of SD, we do look at the kernel of the map from HD SD to HD of a point, and then it would be a uniform statement.
Okay.
All right, let's work up to S1. And if you remember the computation of the homology of S1, what we did there was to look at first an excision statement and then at 2 long exact sequences. Let me recall the excision statement, but let me recall it in the more general form, not just for S1, but for the d-dimensional sphere right away. So what we had there, or what we considered, was HD of SD dd plus, which is just the upper hemisphere in the d-dimensional sphere. Now, if d is at least 1, which I want to assume now, then by the long exact sequence of SD and dd plus, we see that the inclusion from SD into this pair induces an isomorphism, just because the homology of d plus d is 0 in the respective degrees. This relative group we identified via the excision isomorphism with d minus and the equator sphere SD minus. And the isomorphism was induced by the inclusion map. And now we can look at the long exact sequence of this pair. And in the long exact sequence, we have this boundary map, which is a map to HD minus 1 of SD minus 1. And in the proof, well, we did it for d equals 1 to be fair, but this part was completely analogous in higher dimensions. In the proof, in the last video, we saw that this long exact sequence of that pair splits into short exact sequences. And if we go one more in the long exact sequence, we would have here HD minus of dd minus. Let's write it. Now need more space here. Let's move it a little bit over there. Right now we would have here h d minus of d d minus. All right, so once more, this is the excision statement that we used in the previous video for d equals 1, but again it's completely analogous. Then if you just look at this part, this is part of the long exact sequence of that pair. And that long exact sequence split into a bunch of short exact sequences. So you can think of a 0 here on the left and a 0 here, and the whole thing splits. In particular, that guy over there is isomorphic to the kernel of this map. Now, what is the kernel of this map? This is just the kernel of the map hd minus 1, sd minus 1 to hd minus of the point, because this dd minus 1 is just a point. Let's put that over there. It's a contractible space. So this is a point. And therefore, the kernel of this map here is the kernel of the canonical map to the point, or the map induced by the canonical map to the point. And what's the outcome now of the whole discussion? The outcome is that HD, SD is isomorphic to the kernel of HD SD minus 1 to HD minus 1 of the point. The isomorphism comes from this composition. Now, if D is equal to 1, then what we have here is what we just looked at. It's H0, S0 to H0 of the point. If D is greater than 1, then this term vanishes, and we just have here HD minus 1 of the sphere D minus 1. So again, if D is greater than 1, we get an isomorphism between HD SD and HD minus 1 SD minus 1. And for D equals to 1, we have to modify the right-hand side a little bit by taking the kernel to the homology of the point. And now we can use that statement to prove inductively the statement we want to make, namely that the reflection map induces multiplication with minus 1 on HD of SD. So how do we do that? Well, we know that on that kernel, the reflection map induces multiplication with minus 1. So all we have to know is that this reflection map somehow is compatible with that isomorphism, and then we immediately get it for H1, S1, and then H2, S2, and so on and so forth. And we have proved the statement. So why is this isomorphism compatible with the reflection map?
So what do you mean now exactly when you say the isomorphism is compatible with the reflection? I guess we somehow have to specify the plane in which the reflection reflects. And I guess if you want to use the induction hypothesis, then you should choose this reflection hyperplane in such a way that the equator is reflected.
Yes, yeah. No, that's important now. So let's look at the diagram. So we have this isomorphism from HD, SD to this kernel. Let me write it again. And okay, what I mean is I want to have a diagram like that. Where here we have this induced map by the reflection. And here we also have somehow the restriction of this map to the equator, and we want to use the induction hypothesis, which should say us that here we have multiplication with -1, and then we conclude that also here is multiplication with -1. And now,
because the two horizontal maps are really the same maps.
These two maps are the same maps, and everything would be fine. But now, as you rightly say, it is important to specify how where is the reflection plane in comparison to the equator plane? Because if you put the reflection, if the equator lies in the reflection plane, then on the right here, we just have the identity. And on the left, we have a reflection. So that's somehow not what we want, because we want to apply the induction hypothesis to the right-hand side. So we want a reflection here. So what you actually have to do is you have to put the reflection plane, which is a hyperplane, orthogonal to the equator. And then this reflection in its restriction to the equator is still a reflection on SD-1, to which we can apply.
So you sort of pick a normal vector in the equatorial plane, and this normal vector defines the plane in which you want to reflect. Yeah,
right. So
it's not a canonical choice, but it's a possible choice.
It's not a canonical choice. Let's draw a picture for S2, something we can still manage. Then we could, for example, put the equator here. So that's my SD-1, which is S1, and the reflection plane could be here. And then the restriction of the reflection to the equator is still a reflection on the circle. So that's how we do it. And now, again, the question is, why is this isomorphism above compatible? And compatible means that we have a commutative square here. And for that, we just have to write again.
Pull it down a little more?
Yeah. For that, we just have to rewrite this isomorphism and view this commutative square actually as a concatenation of a few commutative squares. So let's write again how this isomorphism, this horizontal isomorphism arises. And it was the following. So HD, SD, going to HD, SD. What was it? D plus. And then excision. D minus. Equator, and then you go with the boundary map to HD SD-1, but actually you land in the kernel of the map, as we have seen, from HD-1 SD-1 to HD-1 of the point, which, if D is greater than 1, is actually just HD-1 of SD-1. That was this isomorphism, and now we want to show this is compatible. So here we have the induced map by the reflection. And let's complete this diagram. And here's the point. So if you can write this reflection here, because the reflection, the way we set it up, look at this picture again. So we have here, in that case, DD plus, the upper hemisphere, and the upper hemisphere is preserved by the reflection, the way we chose the reflection plane. The same for the lower hemisphere, D minus. Therefore, we get a map of pairs. Back to the diagram, get a map of pairs from this pair to that pair. So we get an induced map, and by naturality, because all the maps here that you see actually commute on the space level, we have commutative square, and the same here.
By functoriality already.
Functoriality, yeah. And here we need, again, the reflection preserves SD minus 1 and is a reflection on SD minus 1. And the naturality of the boundary homomorphism gives us also this commutativity. So everything is commutative, and that's the compatibility of this isomorphism that we seek and which gives us, via the induction hypothesis, the statement.